It's a real pleasure to welcome Vecchi to our speaker series today. He started out as a mathematician from Rutgers with a BA and then got on to get his PhD at the University of Washington in physical oceanography in 2000. Then after postdoc, he spent basically his time between Princeton in various roles at NOAA at the Geophysical Fluid Dynamics Laboratory. And for a little bit more than a year, actually, he now has been a professor here at Princeton, both in geosciences and at the Princeton Environmental Institute. His work is on climate dynamics and ocean atmospheric coupling, looking at climate variability and change and its effect on hydroclimate and extreme events, and looking also at climate and the downscaling to regional effects. He's extremely well published in journals like Science and various nature variants, climate change, nature, geoscience. Just to give you an idea about his both volume and impact, his H index is 61, his I index is 133, with well over 17,000 publications. Without much further ado, he's going to talk today about past and future hurricane activity.
Thank you.
Take it away, Gabriel.
So, well, thank you for hosting me here. This is great. I'm glad to have the opportunity to come all the way up the hill and cross Washington. So today I'd like to go through a brief discussion, or maybe not so brief, about hurricane activity and how it has changed, or how we think it has changed, why we think it's changed, and then what it is that we expect in the coming decades and century. And these two sets of questions are interwoven. Some of our expectation about the future comes from our understanding of what drove the past. And so it's really important for us to be very confident, or at least try and be as confident as we can, about what it is that happened in the past and why it is that happened, in order for our predictions to be reasonable. Now, many of you, most of you, some of you, I don't know, were here in Princeton in 2012 when Hurricane Sandy came by, Superstorm Sandy, by the time it went over us, because it was no longer officially a hurricane. But you are probably have some level of firsthand experience about even some of the inland impacts of a hurricane. Hurricanes can have substantial impacts even far from shore, but some of its most devastating occur on shore. Here is the famous roller coaster that went into the water, and the Mantlocking bridge exit, where you have a Google Images picture before and after Sandy went by, and you see that there's a new waterway between the bay and the ocean. So even up here, even this far north, we can have substantial impacts from hurricanes, although some of the more notable impacts of recent have been further down in the tropics. So just to put a thing in, put what's been happening recently in context, this is a time series from the National Hurricane Center's data. It's called the HURDAT data set, the Hurricane Database. And what is plotted each point here from 1851 to, in this case, I believe it's 2016, is the number of major, and this is major defined using the Safer-Simpson intensity scale, which categorizes storms based upon their maximum intensity, maximum wind speed. And the idea there is that although the impacts of hurricanes are complex and varied, maybe considering winds as a summary allows us to maybe group storms into more impactful and less impactful. And so major hurricanes are those categories 3, 4, and 5, or 50-meter-second winds and larger. 50-meter-second winds about 100 knots. For those of you, it's fast, it's uncomfortable. Beyond uncomfortable, if something gets picked up at 50 meters a second and hurled at you, you will not be happy about it, but it won't be for very long. Now this definition of major, of course, is a little bit, it's useful, but it fails to really capture all the ways that hurricanes can impact us. Because if you see over here, there is a peak in 2005 with 4 major hurricanes making landfall in the United States. That includes Katrina. And then afterwards, there's what was up till last spring, or maybe last August, referred to as the hurricane drought in U.S. landfalls. And during that hurricane drought, Sandy and Irene both had huge impacts over the east coast of the United States, but they were not qualified as major because they did not meet this threshold of 50 meters a second. So there's a little bit of arbitrariness here. It doesn't capture all the impacts of hurricanes, but it's a start. So what you should see is that many years there are no major hurricanes making landfall in the United States. Often there's one, rarely there is two, and very, very rarely is there three, and once there was four. And a question is, for us, what caused these variations? Is this just some process completely unpredictable where you just say every year you're just drawing from a random distribution, or is there some sort of predictability here? Can we think of ways to make outlooks for the future on this data? Now, this drought over here, it was really a topic of the news. It was a topic of a lot of scientific literature until August of 2017, which, if you recall, was a very active season. We had Harvey, which had very intense rain impacts over Houston, parked itself just offshore of Houston, and the onshore winds were aimed right at the city. We had Irma, which was very impactful across the Caribbean and the Antilles and making landfall in Florida. Fortunately, the track of Harvey the eye went largely over Florida. Had it not, storms spin this way, and had it tracked off the west coast of Florida, the way the winds would have blown would have given us a huge storm surge going into Tampa Bay, into the city of Tampa. So little track shifts of 20, 30 miles an hour make the difference between a really devastating storm and something that is almost unfathomable, which was what Irma could have been. And then, of course, Maria. Puerto Rico is still recovering and dealing with the impacts of Maria. I heard that the federal efforts to put power back on in Puerto Rico has largely ceased, although power isn't fully back on in Puerto Rico. So these impacts of hurricanes, although the occurrence of a hurricane is very abrupt, it passes over a place in less than a day. Well, not for Houston with Harvey, it lasted a few days there. But the impacts, the outcomes can really have long-term consequences. So in 2017, the story changed. We no longer were talking about the drought, although the papers that were in the publication process talking about the drought did get published. And now there's a lot of the zeitgeist has flipped again, and we're thinking about, is this global warming? Did global warming increase the odds of 2017? And I have two dots there, the big red dot, which is the official U.S. mainland landfalling, and because as we know, Puerto Rico is an island, very, very far away with oceans in between us and it. And so it is that little faint dot, that's Maria. So there's been a lot of U.S. landfalling hurricanes, and we want to know why. Now, it's not just in the North Atlantic that there are hurricanes, and not just in the United States that there are landfalls. I don't know how many of you have seen that Onion piece. It came out, I don't know, maybe 10 years ago. Large landmass south of Texas saves Texas from intense hurricane, right? It's sort of the perspective often in the United States that when a hurricane makes landfall in the Caribbean and Central America, that's somebody else's problem. But but there have been really, really impactful hurricanes. In 1970, there was a big, the Ebola cyclone, over 500,000 fatalities in what was then East Pakistan. And as I understand it, there was already tensions between East and West Pakistan, but this really helped tip the balance. And now we have Bangladesh and Pakistan. They've separated. Then in 1975, there was Typhoon Nina. This was the Ebola cyclone was largely a storm surge fatality. 1975, you had Typhoon Nina. And you had over almost 250,000 fatalities in mainland China, and it was due to big inland rain and successive dam failures, which led to fatality. So there's a lot of wind is one way that we measure storms, but you can start seeing that a lot of the impacts have to do with water, not necessarily directly wind, although some of the water impacts are mediated through wind, right? Storm surges in part blown by the wind. Oh, and I don't know what I did. I'm not going to touch this. Oh, no. There we go. All right, I'm going to go with this. And then in 2015, in the Western Arabian Sea, there was what up to then had been unprecedented. 2 late season. In the West Arabian Sea, there are 2 seasons for hurricanes, one before the monsoon, one after. 2 late season hurricanes, major hurricanes, and then made landfall in Yemen. I was unaware, and many of us were unaware of anything recorded like this. Since then, I've made acquaintance with somebody here at Princeton who's an expert in sort of Yemeni history, among other things, and I'm going to go follow up with him and see if there's any historical evidence going back longer term. All right, so I've been talking about tropical cyclones, just get us all centered. Tropical cyclones are large-scale storms that rotate. They're symmetric. As you can see here on these maps, if you see these, sort of the clouds are very symmetric radially, as opposed to our winter storms that pass over the United States, which are much more asymmetric, comma-shaped. And they form over warm oceans on our planet. I put warm in quotes because there's no absolute threshold for warmth. That'll be one of the cases I'll try and make. And they exist because of a feedback between evaporation, wind speed, and rainfall. So the ultimate source of energy for these storms is the condensation of water in the column of air right above the center of the storm. You condense water, you release heat into the atmosphere. That expands the atmosphere, lowers the pressure. And you have a low pressure that drives a cyclone. And then when you have that drives strong winds. Those strong winds evaporate the water underneath the storm and converge water that give you more water to fuel the storm. That's sort of the feedback. And they have a number of local names. A tropical cyclone in general, it's what it's called, although if it happens in the Atlantic or the East Pacific, it's known as a hurricane. If that East Pacific storm crosses the date line, it becomes a typhoon when it's in the West Pacific. And in the southern hemisphere and Indian Ocean, they're known as cyclones. But it's exactly the same phenomenon, just happens to live in a different place. So those are the things we're looking at. If you look at the distribution of genesis, so this is over the period 1979 to, I believe I did 2010 in this plot, is the location of where storms were formed in the little blue dots. And the shaded area with the yellows and reds indicating warmest waters is the surface temperature of the ocean where those, well, everywhere. And what you should notice is that, well, there's 2 patterns. Anybody see one pattern? They're not randomly distributed, but do you see anything here? There's nothing at the equator. So these storms draw their rotation from the rotation of the Earth, and the equator is parallel to the axis, so it doesn't get that. And then the other pattern you should see, I hope you would see, is that they happen over the warmest waters. So we need warm water and we need rotation. Those are 2 sort of necessary conditions, but it's not enough. Cyclones need a calm environment. They need, there's this idea, it's vertical wind shear, which is a difference in wind speed with altitude. Too much vertical wind shear will tend to rip a storm apart. Although just the right kind of wind shear, Morris Bender, they wrote a nice paper where just the right type of wind shear will actually help keep the storm alive. But anything else is bad for the storm. And you want a moist middle troposphere. So there's a number of factors. We have fundamental theories for hurricane, well, for aspects of it. Most of the rest is either heuristics or quasi-physical heuristics, where, but for this is real theory, and it is the theory for potential intensity. It's the theoretical upper bound on the intensity of a hurricane, and the way it can be understood, the way you want to derive it, it takes days and days to really understand what's going on. But the way it can be understood is using a Carnot heat engine analogy, where there are two terms. This term here on the left, which is surface temperature minus upper atmospheric temperature divided by upper atmospheric temperature, is an efficiency term. It's how efficiently the storm, the hurricane, this heat engine converts energy into motion. And then this K star minus K is a difference between two enthalpies, two entropies, two heats near the surface of the ocean and right above it. And what that is the fuel source term. When you have a lot of fuel at the surface of the ocean, then you can start driving this heat engine. But the rate at which energy is converted into motion is limited by this efficiency term. And so that's how you can think about it. And these two terms, as you look at them, the fuel term, the one on the right, increases as the ocean warms. And oftentimes when we start thinking about the impact of global warming on hurricanes, at least initially for me and for many people intuitively, we think about this fuel term. You warm the planet, you have more fuel, you should drive stronger storms. However, there's also this efficiency term. And this efficiency term does increase as you warm the planet, the same way you can run your engine hotter, you can run your engine more efficiently, right? That's why you want to, when we're thinking about ceramic engine blocks, other things. However, it also decreases, this efficiency decreases as the upper atmospheric temperature, the bath temperature, gets warmer. So you notice that your car runs more efficiently in winter than in summer. Is because the environment is colder in winter than in summer. The engine to environment temperature difference is larger. And so the best environment for a storm is a warm surface in a warm upper atmosphere. The issue with that is, in interpreting global warming, that sure enough, global warming does warm the surface, but it also warms the upper atmosphere. And it warms the upper atmosphere by more than it warms the surface. And that's because the upper atmosphere reflects both the warming, the sensible heating of the surface, and also the increased moisture in the atmosphere. Moisture is energy in the atmosphere. Okay? So intuitively, thinking not much at all, you might think that the fuel term is the only term to pay attention to, but this efficiency term does come along. So this is how I got into hurricanes. It was this figure by a paper by Carey Manuel. It was, I think, from the point of view of finding correlations and trying to infer them for causation, I found it amazing. It was originally a paper in 2007. This is the update from paper from 2005. This is the update from 2007. Shown in blue is the surface temperatures of the ocean in the tropical Atlantic, where hurricanes form, what we know as the main development region, the MDR. And starting in 1950s to the mid-2000s, they're low-pass filtered to highlight the low-frequency variations. You see that they kind of dip down and they come back up with wiggles. What is incredible about this figure is the green line, which is the power dissipation index. It's the sum of the wind speed cubed across all records of hurricanes in the Atlantic. So it's an aggregate measure of hurricane activity. And they look like each other. Every time I look at this figure, I have to figure out which one is which because they look so much like each other. The R squared there is 0.75. 75% of the variance is explained by one, is explained in the other. In geosciences, we never see correlations this good. There's just too much going on in the system. And when you see this large of a correlation, it just makes you think, well, there's got to be causation here. These have to be causally connected. And thinking, well, the fuel term moves up and down like this blue line. So maybe that green line is reflecting the fuel term. And this is when I was thinking about it, and then I said, well, a lot of us were thinking, wait a second, okay, if that fuel term looks like surface temperature, we know surface temperature to continue to warm. 2005, we had just had 2005 with Katrina and Rita and all those storms. Holy smokes, what's going to happen in the future? And so we started asking the question because it really looked like a dramatic period where we're going to go into some unprecedented hurricane activity. However, and this is a summary plot that I made after doing a bunch of research with my colleagues, Brian Soden and Kyle Swanson. Atlantic surface temperatures aren't the only way to understand hurricane activity. And to illustrate that, I'm just going to plot, in the black line here is a that hurricane activity index that Kerry Emanuel plotted, I replot it here both ways. The red line is surface temperature in the Atlantic, so it's an equivalent plot to what Kerry Emanuel showed. And what you should see is, again, that they match really, really well. So that surface temperatures are a good explanatory variable, at least over this period for Atlantic hurricane activity. But in the bottom, I will plot a different potential explainer. And what's shown here in blue is this quantity which we call relative Atlantic surface temperature. And what this is the temperature in the tropical Atlantic minus the temperature over the entire tropics, average over entire tropics. So it's how warm is the Atlantic relative to the tropics as a whole. From the correlation coefficient between the blue line and the black line and the red line and the black line is the same to the, I believe, fourth significant digit. And we picked the averaging area so that that would work out. We could make one slightly bigger, slightly larger. And the third significant digit, we really, because we wanted to make the point that from the point of view of correlation and inferred causation, the evidence for the red and the blue is the same. So how do we separate them? And do we care to separate them? Before I explain to you why we would use the blue one, I'm going to show you what the implication of each one is. So we have a relationship here, statistical relationship that links patterns of temperature change to hurricane activity in black, and on the top that links total temperature in the Atlantic to hurricane activity. Let's take our global warming simulations for the 21st century and put those statistical relationships in and see what it tells us the future should look like. We have two lines, two families of possible futures. The top one is taking the statistical relationship over the 1950 to 2007 period and projecting it forward using dynamical climate models. And what you see is a future that by the end of the 21st century, the lower bound is higher than anything we've seen at the end of the 20th century. And that includes the 2005 hurricane season with Katrina, Rita, all those impacts. And so it's really one of those futures that you have to start asking yourself, can society handle this and how would we handle it? However, you look at the bottom plot, and it's a future that looks a lot like the past. There's active periods and inactive periods. And what that reflects is that although the planet is going to warm, the Atlantic will sometimes be warmer, sometimes be colder than other oceans, and this thing will slosh around. So, two very different futures, equivalent present statistical relationships. That one makes sense intuitively, and also makes sense from the fuel term in hurricane activity. Why did I put this one here? Well, in order to do that, I'm not going to go through the whole physics. It's not very complicated atmospheric physics, but I'll just explain it to you from a simple point of view. There's a lot of evidence that the temperature of the upper atmosphere is controlled not locally. So if I want to know the temperature in the upper atmosphere in the tropics, say I'm sitting in Puerto Rico, I shouldn't look at the surface temperature locally. Rather, I should look at the surface temperature globally. And the reason is that the tropics, because they're far away from, the surface is parallel to the axis of rotation, so you can't sustain gradients, there's no boundaries. So any temperature signal will rapidly make its way all the way around the atmosphere. So if you want to know upper atmospheric temperatures anywhere, just look at the tropical average temperature. And if you look at satellite data, this is supported. If you look at models, this is supported. And so what Atlantic relative temperature is a stand-in for is the surface temperature in the Atlantic minus the temperature in the upper atmosphere. Right? So this is a lot like that efficiency term. And so what this term is really, this one would depend on is the efficiency term the main driver. Right? It's a vertical gradient term. This is expressed as a horizontal gradient, okay? And then this is just a local temperature term. Okay, so they both are equivalent over the past 60 years. How can we tell them apart? We could wait 40 years, but that's not really, I mean, that's boring. Or we could travel back in time. So one way to travel back in time is these hurricane records. Remember I showed you with data going back to 1851? Well, why stop at 1950? Let's go back to 1870s. And the reason I'm not going to go not to 1851 to 1878 is that in 1878, the Congress tasked the U.S. Signal Corps, which is the predecessor of the National Weather Service, with tracking all storms in the Caribbean, in the Atlantic, and the Gulf of Mexico. And so the Signal Corps and now the Weather Service have been doing the best they can at tracking those storms. So what we have here is a series of stacked time series starting in 1878, moving to the early 2000s. They're all low-pass filtered to highlight low-frequency variability. The top plot is global mean temperature. Just to set our ground, global average temperature has warmed. I think it's unambiguous that the planet has warmed over the past century. That's reflected over there. There are periods where the planet has warmed more rapidly, periods where the planet has warmed more slowly, and even periods where the planet has cooled temporarily. But on the long time scale, the planet's warmed. That's global warming. Large part, that's due to increasing greenhouse gases. Tropical mean surface temperatures, shown in the next green line, look a lot like global temperatures, although they have a lot more wiggles. And that's because you're looking at a region, you're not looking at the globe. The globe, there's a lot of cancellation of all these variations. But there is a significant trend. The next plot is, if you go to the National Hurricane Center, download the hurricane database, and just count the number of storms every year, the number of hurricanes every year. It's almost a trivial task. I managed to do it. I'm sure you can too. And what you find is an incredible correlation between the number of Atlantic hurricanes recorded and Atlantic surface temperature. They both share, in a normalized sense, the same trend. They have very equivalent variations. And so it's really sort of tempting to interpret this one as arising from that one. It doesn't make sense to interpret the surface temperatures arising from the hurricanes. You can work out why not, but trust me, you can't. So if there's causation, it's going from surface temperatures to hurricanes. But that's not the only possible interpretation. That's the number of recorded hurricanes. The number of recorded hurricanes is not the number of hurricanes that happened. It's the number of hurricanes that happened and somebody recorded, right? This is two very different things. And the reason it's different is here's a map of typical hurricane tracks in the Atlantic. Here's Africa, South America, the United States. And here, on a similar projection, are typical ship tracks in the pre-Panama Canal era, the Panama Canal era to World War II, and the World War II era to 1965, which we know as the satellite era. That's when we have monitoring with satellites. And what you should be able to see, particularly in the pre-Panama Canal era, these look like mirror images of each other. Right? This is like a negative space of that. Now, it wasn't that the ships were avoiding the storms. It's just that it doesn't, economically, it didn't make any sense for the ships to go over here and then cut back against the winds to sail underneath the two capes. Right? So if they were going to the Indian Ocean, they would hug Africa, go just east of Brazil, and then cut across. In the same way if you're going down south of South America. So ships were not going where storms were typically. And so what we did is we built a simulator of what storms would have been seen or missed by the ship tracks of every year, going back from 1878 to the beginning of the satellite era. And you can then build up a probabilistic assessment of how many storms were missed. And what you end up with here is this is now, the red line is the number of hurricanes going back to 1878 adjusted for likely missing storms. And if you see on sort of decadal timescales, these two are very similar, but the difference is they have very different trends. One of them has a positive trend, an increasing trend. The other one has a slight, non-significant decreasing trend. Now what that means is, comparing these two, is that the recorded hurricane increase in the Atlantic is entirely consistent with what you expect from changing observing practices. So we can't say hurricanes increase in the Atlantic, even though recorded hurricanes very definitely increased in the Atlantic, right? It could be that we just missed them. Unfortunately, if we miss them, we're not going to find them. They're just not there. And so that's an uncomfortable position to be in. Now, what we can do is we can look at U.S. landfalling hurricanes. U.S. landfalling hurricanes exhibit a slight negative trend like the adjusted count, while the raw hurricanes exhibit a positive trend. We're now in a simpler world if we keep the red line, because we'd only have to explain why basin-wide change, not why the fraction of basin-wide making landfall in the U.S. went in different directions, right? So, and then finally, if we look at relative sea surface temperatures, it's better related to adjusted hurricane counts than it is to raw counts. Meanwhile, tropical surface temperatures, tropical Atlantic surface temperatures are better related to raw counts. So if you look at the century scale data, the evidence is in favor of Atlantic temperatures if you believe that we've seen every hurricane that was there. If you take into account changes in observing practices, then the support is more now for the pattern of ocean temperatures mattering. So that's one bit of data. This is some new work that we've done. We've extended this analysis to look at now major hurricanes, category 3, 4s, and 5s. And perhaps unsurprisingly, what we find is that if you look at the recorded number of major hurricanes, this thin gray line here, there's been an increase over the 20th century. However, that is, again, entirely explainable by changing observing practices. So we haven't had a recorded increase that is large enough to exclude the potential that changing observing practices cause it. So it's not clear that hurricanes have actually increased in the Atlantic. All right, so that's observational evidence. The other bit of evidence that you can bring to bear are models. So everybody runs models, everybody builds models. I believe the models we use are probably different from many of the models you use. So they're not fundamentally statistical. Rather, they are discretized representations of the physics of the atmosphere, ocean, land, and sea ice run on a computer. However, they do include statistical elements, which we call parameterizations. These represent things that we either don't understand fully, like the conversion of water vapor into droplets in ice inside clouds, or which happen at scales much smaller than we're able to represent, such as atmospheric convection and oceanic convection. However, we can run these models in a number of configurations. This is what we do, what is often done. Some of you have probably looked at the IPCC models, or the CMIT models, and these can tell us something about the change over the 21st century. However, until very recently, computing power limited the ability of these models to explicitly represent hurricanes. So this orange graticule here is 2 degrees by 2 degrees, and it's sort of representative of the capability, the resolution of models up to about very recently. And this is Hurricane Rita, one of the largest hurricanes in the Atlantic. And what you can see is that inside a single grid point, you'd have to represent the hurricane eye, sort of the initial rain bands and eye wall, and then even some of this outer rain bands. So there's no way that with a 2 degree by 2 degree model, where you can only have one number in here for cloudiness, you're going to represent this hurricane, right? Because you have descending motion here, ascending motion there, descending motion there, ascending motion there, and you get one number to represent it all. It's not going to be represented. However, what these models are able to do is tell us about the large-scale environment in which these hurricanes are operating. And so that's what we did. We looked at how these models say in the 21st century, the large-scale environment in which hurricanes would behave, would evolve. And so on the top plot is the average across 21 global models of surface temperature changes in the tropics at the end of the 21st century relative to the present. The red shading is places that warm. And so what you should see is that everywhere in the tropics is projected to warm, and that's due to increasing greenhouse gases. The bottom plot, this is a plot that Brian Soden and I were going to do, and we said, oh, we need to calculate potential intensity. So what this is how potential intensity changes, the theoretical upper bound on hurricane intensity. And so when it was time to make this plot, I told Brian, you're the atmospheric scientist. Could you do this calculation? And then a couple weeks later, he emails me and calls me back. He's like, listen, I don't have time. I can't do this. Could you do it? And then I do it. And I can't get this right. There's no way I can get this right. I keep finding potential intensity decreases, even though I know the whole tropics warms. And I'm like, no, Brian, I can't do it. I'm busy. Could you do it again? And we're going back and forth like that for a while. And then finally we come, over a beer. We're like, listen, the reason I asked you to do it is that I can't do it right. I keep finding decreases. He says, me too. And so we realized that we were actually doing it right. And what was wrong was our expectation, not the calculation. And what's shown here is the change in potential intensity at the end of the 21st century, with blue colors being areas where potential intensity, that is a theoretical upper bound on the hurricane intensity, decreases, and the red colors are where it increases. And even though the planet as a whole warms everywhere, about half the tropics has a potential intensity decrease and half the tropics has a potential intensity increase. To understand this, contoured over here with solid lines indicating places that warm more than the tropical mean, and dashed lines indicating places that warm less than the tropical mean, is the surface temperature change, or the pattern of surface temperature change. And so what you can see is potential intensity change is not controlled by whether the tropics warm or cool, but by whether they warm or cool more than the rest of the tropics. It's a pattern question, and unfortunately that makes it a much harder question. Connecting CO2 to tropical temperatures is really straightforward. It doesn't take that much physics to do it. Connecting CO2 to patterns of temperature change is incredibly difficult because it involves clouds, it involves atmospheric dynamics, it involves ocean dynamics, and the interaction between all of them. And so we've now defined a much harder problem. Now, what do these models tell us about the 21st century? I'm just going to give you this summary and only show you some results. I'm not going to show the top one, but what we've come to learn is that if we want to look at the end of the 21st century, radiative forcing matters, that is CO2 changes, but also internal variability. The chaotic variations of the climate system are important, and they're important even at the end of the 21st century. So we're not going to get away from internal variability, and we need to account for it whenever we do our calculations. The greenhouse gas signal in TC activity, tropical cyclone activity, is unlikely to emerge until the end of the 21st century. So what we're going to see over the next half century is going to be dominantly, or it's going to be sufficiently contaminated by internal variability that we won't be able to clearly discern the impact of CO2. That does not mean that there is no impact of CO2. It just means that we're going to have to work and make policy in an environment where there's a lot of uncertainty, right? And so that's just inherent. Non-greenhouse forcing, aerosols, little particles in the atmosphere, and internal variations are going to be dominant in the next few decades. All right, so I said that until recently, global climate models couldn't represent tropical cyclones well. The resolution wasn't there. There's recently been some sort of groundbreaking advances in representing high-resolution atmospheres, in part led by S.J. Lin's group at GFDL. And one of the results is this model, where you show observations, just to remind myself, on the bottom. These are tracks. And the top plot are the output from the model. The shading, the color of each line tells you the intensity of the storm, and the lines tell you the track. And what you can see is that this climate model is able to recover a pretty good sort of representation of the types of tracks and storms that we see on our planet. There's still deficiencies. It makes too many storms in the South Atlantic. Makes too many storms in the southern hemisphere. I think some of these issues with the storm tracks in the southern hemisphere extending too far south are because the meteorological center stopped tracking the storms down here. It's not because they don't make it down there. Anyway, what does a model like this tell us about the end of the 21st century? Well, shaded here is the projected changes in major, category 3, 4, 5, hurricanes, with red indicating places where the model shows an increase in major hurricane days. The blue, not blues, but blue, indicating the place where it shows a decrease in major hurricane days. And then the little white X is places where it's not statistically significant. What you should see is that the only significant changes projected for the end of the 21st century are positive. So where the model says it thinks it knows what the changes are going to be, those changes are for increases in the number of major hurricanes. The number of major hurricanes, the increase in number of days with major hurricanes at each grid point can be large, in excess of 100%. So by the end of the 21st century, this model is telling us that we should have substantially more major hurricanes. Another question that we asked with this model is the question related to rapid intensification. Tropical cyclones often or sometimes undergo this process known as rapid intensification, where their intensity changes by a large amount over 24 hours and by almost a category or more. Now this is, number one, very hard to predict from weather timescales, but number two, can be very impactful, because what can happen is somebody goes to bed after seeing the weather forecast and you're expecting a category 2 storm, which is impactful but not devastating, and overnight the storm does rapid intensification and you're facing a category 4 storm. And so it makes response to these storms, especially if rapid intensification happens near shore, very, very problematic. And this is a percent change in rapid intensifying cases in this model at the end of the 21st century. Wherever there's a significant change, it's positive and it can be upwards of 100%. So we're looking at the end of the 21st century, a situation where we're going to have stronger storms according to this model, and those storms are going to approach that high intensity very rapidly. And so some of the typical mechanisms that we have in place right now to deal with storms may not necessarily apply. However, there's a lot of advances in weather forecasting, so maybe by the end of the 21st century, this won't be an issue. But if this were to happen today, it would be an issue. Our weather forecast systems aren't yet ready for this type of world. Now, this is just one model. Here's a figure which is a compilation from a number of studies, including a study led by Morris Bender, by Tom Knutson, by others, where it shows what different models say should happen at the end of the 21st century in the Atlantic. I showed you a case where the model said it should increase, hurricane activity should increase. However, if you look at category 4 or 5 hurricanes, these are the most intense hurricanes, there are models that actually say that in the Atlantic they should decrease. So there's a fair deal of uncertainty. I showed you one case, but there are other cases out there. There's the potential for a 250% increase in one case and what is almost 100% decrease in another case. So we've narrowed it down. Now, what you do see across this model ensemble is that the models are much more sure that the weak storms will weaken, and for the stronger storms, there's more of a tendency to increase. What this reflects is a combined effect of two things. One, a global frequency decrease, and two, an increase in the typical intensity of the storms. And what that then results in is, depending on the relative ratio of those two, you'll either have the frequency dominate, so then the most intense storms will decrease, or the intensity dominate, and then even though the frequency goes down, you'll have so many more of the intense storms that you have more intense storms. Now, I joked about us not having a lot of spread over here, a lot of uncertainty. That spread is actually helpful. But what we can do is we can look not just across those studies, but we can look across this dozen studies around the world, and we can say, okay, what do these models project about North Atlantic tropical storm frequency? And so this is the North Atlantic tropical storm frequency projections from minus 100% to plus 100% from all the studies that were available at this time. And what you see is that you have a range now between minus 90% and plus 80%. So good again. And you say we don't know anything, but it turns out what we do know is something. Here is a statistical model where the two predictors are Atlantic and tropical mean sea surface temperature, that is relative sea surface temperature, and 60% or 55% of the variance across all these studies, each one using different models, different forcings, all sorts of different other things, can be understood in terms of the pattern of surface temperature change that they put inside this model. So if we could predict the pattern of surface temperature change, we could predict Atlantic hurricane frequency with a lot of accuracy. So bad news, we don't know anything right now. Good news, we start knowing what the right question to ask. It's not whether the tropics is going to warm, but whether the Atlantic is going to warm more than the rest of the tropics or not. So I'll just skip this over. Now, I'm going to go really fast, excuse me another 3-4 minutes, because I spent a lot of time answering the question that I and many of us thought was really important starting about 10 years ago. Is basin-wide activity in the Atlantic going to increase or not? What's the impact on basin-wide activity of global warming? And the more and more I thought about it, especially recently, that may not have been the right question to ask. Basin-wide activity largely occurs in the basin. Many of the big impacts of hurricanes are tiny little events, very concentrated in space and time, that have a unique story. And what we should perhaps be asking is questions about those extreme parts of the extreme events. Just to illustrate that, in 1992, we had, I think it was the most inactive season within the most inactive epoch of the system. And so you can see here, these are the storms that happened in 1992 in the Atlantic. Most of them out to sea, they're weak, there's almost no named storms. But there was one, the first one of the season, Andrew, which caught a swath of devastation across the Bahamas and Miami and South Florida that is still in people's memory today and was really, really impactful. So in 1992, the question wasn't were there going to be more storms in the Atlantic or not. It was, what's the storm that cuts across South Florida going to do, right? And so even though we don't know what basin-wide hurricane activity may do in the 21st century, we can say with a great degree of confidence what certain extreme characteristics of storms will do. And the reason is there's some very simple physical relationships related to warming that we can exploit. One, the Clausius-Clapeyron relation, which tells us that warmer air holds more moisture. So not knowing anything else, which is what I just said, we don't know what frequency is going to decrease, so we don't know anything else. Not knowing anything else, a warmer atmosphere will give you rainier storms, right? That's one prediction we can make. And so unless we have great confidence that hurricanes are going to decrease and landfalling hurricanes are going to decrease, they're going to be rainier when they make landfall. And you start thinking about what the impacts are on society. Well, we've built a lot of our water processing and water dealing with, I don't know, what do you call that? It's not the right word, Jim. Storm management, not water dealing with facilities, but storm management. Our storm management has been designed with some thresholds. We're not going to design for the infinite storm. You say, I'm going to design up to this point. But if your 100-year storm is changing over time when it comes to rain, that becomes an issue. The other one is, this is really, really simple. You can do this experiment with a glass of water. If you heat water or you melt ice into it, the water level will rise. We are confident. I'm not confident about many things. I always hedge word everything I say about the 21st century. Sea level will rise over the 21st century. It will. It will rise more certain places. It will rise less other places, but it will rise. And so the same storm will give you a bigger storm surge. And so this is something we need to keep in mind. In fact, we think that there's evidence already to say that Harvey was made wetter by global warming. So Harvey was an unusual event. It was meteorologically very special. But there's substantial indications that the odds of something as strong as Harvey have increased since 1900 by something between twice to 5 times as much. And that the amplitude of the rain of Harvey was made something like 10% more because of global warming. Now, there was a number of other factors that might have also changed the probabilities and changed the characteristics, but the warming is starting to make its way felt, perhaps not in the frequency of storms, but yes, in the character of the storms when they hit us. And we expect that this is going to continue over the 21st century. The other thing is that sea level, again, to say sea level is rising and will continue to rise, I want to put this plot up because I think it's beautiful. This is, the black line is an estimate from satellites of sea level across the globe. Really complex, a lot of sort of structure there with these peaks and these troughs, and we think we know what these are. And a big increase. The blue line and the red line are two independent from each other and independent from this black line estimates of the sea level rise due to melting land ice I believe that is the blue line, and the sea level rise due to warming oceans, the red line. The purple line is just the sum of those two. We've closed a sea level budget for our planet. It's amazing. We have satellites that we can interpret to close the mass, density, and volume balance for our ocean. We know sea level has risen. We know why it has risen, and those things are going to continue in the 21st century. Anyway, just to summarize, it's premature to conclude that we've seen Atlantic tropical cyclone change due to CO2, although the impacts of the cyclones may already be changing due to CO2. Models allow us to estimate hurricane activity changes. We've come to learn that the pattern of surface temperature change is the dominant thing to keep in mind, not just the overall warming. For the end of the 21st century, maybe fewer storms in the North Atlantic, probably stronger, and whether we have more of the strongest or not will depend on the offsetting effect between those two. I didn't talk much about this late 20th century hurricane drought, and I didn't talk at all. And this is really the take home. There's a lot of uncertainty and really interesting physics to be done up here. But if you're starting to think about policy and what society is at risk for, the per storm precipitation increases are simple to understand. Sea level rise is simple to understand, and its effects, at least to zeroth order, are simple to understand. And demographic changes, I'm not a demographer, but I've met people, and they tell me that the movement of people to coasts is a pretty robust thing and is likely to continue. And so as all these other factors are tilting the odds against us, so are some of our demographic changes. And so how do we make decisions in the coming century? How do we incorporate some uncertain information with some more certain information to make good decisions? Well, it's not my job yet. Thanks. Yeah.
So, just so I understand, the reason the pattern of temperature differences matters is because the broader change reflects the higher...
The upper atmosphere?
The upper atmosphere, therefore the difference, and therefore...
Yeah.
So why do you think you found... why was there essentially the same pattern of change recently in total... in surface warming and in the difference? Because you said basically both, you could put these lines on and,
yeah,
and they seem to track each other, and it doesn't seem really coincidental.
No, it's not. Oh, please don't go away. If you look, no, this is not the right way to look at it. If you look at the red line and the blue line, they're very, very similar. But if you start teasing them out, the red line starts out slightly below the equator, and the blue line starts out slightly above the equator. The reason they look so similar is that the variations, so the wiggles, have been larger over this past, say, 50 years than the trend. And so when you look at this time series, or when the statistics look at this time series, they pull out first these wiggles, and those have been those are local in character. And the overall warming is global in character, and that is picked out second. So, did that help at all?
Yeah, but what you're saying is that they just look like they're correlated with each other, not really?
Well, they definitely are correlated with each other because they share one element, right? So, this is A minus B, this is A, and B is the trend, right? And so, what you're seeing is that B, at least over this period, is small. But when you go to the end of the 21st century, the trend is big. So, yeah, back.
So I'm not a scientist, and I find this particularly compelling, your data, having lived in New Orleans and been there during the year of Katrina. And one of the puzzles that we experienced that year was that the earlier hurricane seasons, first of all, there was a historically early hurricane, and it was said to be barely a Category 1, that actually inflicted quite a bit of damage. In the years preceding Katrina, having been there for 20 years, in the years immediately preceding Katrina, our evacuation activity increased as we saw these storms coming in that had the potential, because you don't know what it's going to hit as. And so my question for you is whether it is also time as you do these analysis to rethink the Saffir-Simpson scale, the scale of the 1 to 5. Because what we're seeing rain events, we're also seeing wind gusts that have the potential to shut down the power grid, which is what happened in a Category 1 storm. So that as when you're informing policymakers, they begin to understand that because it's not a Category 5 or it's not 3, 4, or 5 potential, it is still, you're doing it with the surface temperature, and as a native, as somebody who lived in New Orleans a long time, which is below sea level, what I'm seeing is people returning to New Orleans thinking that Katrina was a one-time event that will not happen again in their lifetime. And you're seeing building and other decisions being made on the basis of these 3, 4, and 5 classifications, rather than the more subtleties that you're introducing into the conversation, which is quite
Yeah, so definitely the Saffir-Simpson categories are lacking. And so James Doney, who is at NCAR, has done a lot of work funded in part by folks in the reinsurance industry to come up with a more relevant but compact way of communicating how potentially impactful the storm is. He's made some headway. Unfortunately, because the more we learn about storms, the more we realize that they have many ways to hit us. I'm not sure we'll ever hit with one singular thing, but you have this trade-off. You don't want the language you use to communicate risk to be so complex that people tune out, but you don't want it to be so simple that people miss the real information. And I think that there are experts in communication out there that aren't necessarily being brought in early enough in the process. I don't know. There should be ways to better do it. The other one is we tend to forget that there are, once a storm stops being tropical, people maybe lose it in mind. And we can see that once a tropical cyclone becomes extratropical, it can have big impacts. So, I think this is a work in progress, and how to communicate this risk is huge.
I think I heard you say that we're getting as much warming in the upper atmosphere as the lower atmosphere, but I thought there was a gradient. I thought we're getting much more warming closer to the surface than in the upper atmosphere.
It's the inverse. We should expect more warming in the upper atmosphere than at the surface. This is known as the lapse rate response. And the reason for this is that the upper atmosphere warming reflects, first, the warming of air near the surface, a temperature warming of air near the surface that then is communicated to the upper atmosphere. And secondly, the increased moisture holding capacity of air near the surface that then is communicated in the upper atmosphere as temperature when that moisture condenses. So you get about 2 degrees of upper tropospheric warming for every degree of surface warming. At least theoretically and in year-to-year variations. There is one controversy, which is known as the tropical lapse rate controversy. If you look at some satellite data, it's not clear that the upper troposphere in the tropics has been warming, although that probably has to do with the satellites. It doesn't have to do with the atmosphere. I think the atmosphere knows physics, the satellites know different physics. Yeah.
If your temperature is higher quickly, isn't it your T0 is increasing higher? Your efficiency factor is less.
Yeah, and so then the storms become weaker. So unfortunately, we'd have to get really into the weeds of potential intensity, and it gets even worse than what you're saying because it's an implicit function. And you have to evaluate something at the radius of maximum winds, and you don't know the radius of maximum winds until it gets really a mess. And the only way to know what potential intensity change is going to be is to actually calculate it. And the other problem with that is that's the speed limit of a storm. And I'm not convinced that the speed limit of a storm is what matters for the speed of a storm. The analogy I think of is Route 1. If you want to think about how fast my car is going, it's not the speed limit. It's how fast I can accelerate in those gaps between when one stoplight turns red and the next one, you know. So what I think is going on at the end of the 21st century in some of these simulations is that the storms are rapidly intensifying. And so they're approaching their speed limit more rapidly. And so between when they're in these really narrow gaps of favorable environment, they can really take advantage of them. But storms are really, really tough. So, everybody good? I can't see anything. Yeah.
Questions to come back to this time series that were very interesting and a very striking correlation. But another way to look at the causation is also look at phase differences among the two. And looking now the blue series with the black, you see, actually for certain event, you look at the blue series is preceding the black now, on the principle that the causation have to precede the effect or the effect to follow. So did you analyze?
Yeah, so what we did was this is only one filtering. We actually analyzed unfiltered data and filtered with different filters.
Like a monthly data.
Yeah, and this relationship holds on all time scales, seasonal and upward. This one only holds for certain filterings. So you have to filter very narrowly to get this relationship. If you make the filter too low, it breaks, and if you make the filter too high, it breaks. And one thing I didn't show, that was the data through 2008, 2007. We've had 10 more years. And this blue line over here is the extension of the data over the last 10 years. And you see that the intensity the hurricane activity has decreased, almost popping outside of the range of where it should be. Meanwhile, again, this is the decrease. The observed hurricane activity is well within the range. Then the other thing that we've learned, there's been a reanalysis of hurricane intensity. And people found that in the 1960s, the storms were more intense than we had originally thought they were. And so the back end of the time series has dipped down, or the front end and the back end has been lifted up in the last 10 years. So I think that the evidence has gone more for the bottom interpretation than the top as we learn more. But we'll see. Yeah. Jane.
The plot with the rapid intensification changes preceded by the plot of changes in frequency, I think. I was surprised that it looked like the changes in rapid intensification were like perhaps more significant than the changes in frequency. Like,
Yeah.
is there a physical reason why you think we might be able to have more confidence in a change in rapid intensification rather than a change in frequency?
No, what I think that reflects is purely an estimate of statistical significance. I don't understand rapid intensification. I don't think there's anyone who, if they're honest, understands it in a general sense. After every time rapid intensification happens for a storm, there is a wonderful story, a just so explanation as to why it happened in that case. But it's one of the hottest topics in hurricane research. And next week there's going to be the American Meteorological Society this is the annual hurricane meeting down in Florida. And I don't, how many dozens of talks on RI are there? I don't know. And so this is more statistically significant. I still don't fully understand it. Yeah.
I think I'll speak on one more.
Okay. Thanks.